All right, this is going to be an intro crash course on how computers work at a really low level. So we're going to learn about transistors, logic gates, truth tables, and how computers add numbers and do math. Let's go. So inside of all computers, inside of phones, laptops, tablets, microwaves, they're made up of millions and millions of transistors. So we can draw out a transistor diagram, looks something like this. And then so here's the power source, here's the input, and here's the output. And we'll label this transistor. And so you can think of a transistor like a switch. So the input turns the switch either on or off, which either allows or blocks the current to go from the power source to reach the output. So depending on how it's wired, it'll either turn the switch on, or turning the switch on or off can either make the output the same as the input, which is a buffer, or the opposite of the input, which is an inverter. So now we're going to write out our logic gates, and we've already got our first two done. So we'll put the diagram over here. And then so the diagram for a buffer is just a triangle. So it has one input and one output. And then this is our buffer. And so we can map what the inputs and outputs are. And we'll write them as zeros and ones instead of on or off, because that's how we work with different logical diagrams and such. So if the input can either be 0 or 1, and so if the input is 0, then the output is 0, and if the input is 1, the output is 1, because buffers don't change it. So whatever the input is the same as the output. And this over here is called a truth table. And so it takes every combination of inputs and then maps them to the output for the logic gate. So we can also have an inverter here, which just looks like the buffer, except for we have this little circle in here. And then this is an inverter. This is also called a NOT gate. So we can make the truth table for our inverter. So we still have the same two potential inputs, 0 or 1. And with an input of 0, it's inverted to be a 1. And with an input of 1, it's inverted to be 0. So if there's current coming in, then there's none coming out. And if there's not current coming in, then there is current coming out. So it inverts the input. So we can also wire multiple transistors together. So we could have them in series. So I'll draw two transistors right here, all lined up in a row. And so now we have two inputs, input 1 and input 2. And then we have one output. And so this is called an AND gate. And so there's our two inputs here and a one output here. And so if both of these are off, then the current can't flow. If input 1 is on and 2 is off, the current can't flow. If input 2 is on and input 1 is off, the input can't flow. So only if both of the inputs are on, then the current can flow through both of them. So we'll make our truth table with our two inputs. And so now we have 4 combinations of inputs. So if both of them are off, the output's off. If one of them is off and one of them is on, the output's off. So only if input 1 and input 2 are on, then the output is on. And so these are wired in series. We can also wire them in parallel. And then so this will be input 1 and input 2. And then we'll wire them together so that this is the output. And then our power source can come in through here. And so now that they're in parallel, if this one is on, then that allows the power to come out. Or if this one is on, then that allows the current to go through, sorry. And if both of them are on, then the current can also go through. So the current goes through if either one or both are on. So the only way it doesn't go through is if neither of them are on. So this is called an OR gate. It's like an AND gate, but it's got the back is a little more curved here. And so these are our two inputs and our one output. Then we'll make the truth table for our OR gate. And so if they're both off, the output's off. But if either one of them is on, the output's on. And if both of them are on, then the output's still on. And so that's our OR gate. So next we'll learn about the NAND gate. So the NAND gate is a not AND gate. So we have our AND gate with the inverter at the end here. This is what the diagram looks like, and this is a NAND gate. And we'll make the truth table for our NAND gate. And again, we have 0, 0, 0, 1, 1, 0, and 1, 1. And so the NAND gate is the opposite of the AND gate, so we're inverting the AND gate. So the output is on unless 1 and 2 are both on, in which case it's off. So it's the exact opposite of our AND gate there. So we also have a NOR gate. You can guess how this behaves and what this symbol looks like. This is our OR symbol with a little inverter there. So this is our NOR gate. And then we'll make the truth table for our NOR gate as well. And so NOR gate is the opposite of an OR gate. So long as none of them are on, then the input is on. Otherwise, it's off. It's the exact opposite of the OR gate. And then we have an exclusive OR, which has an extra one of these curves in the back there. And we label this XOR. And you can think of the exclusive OR like when you order something at a restaurant and they say, do you want either a side or a drink? They don't mean that you can have both. You can get one or the other, but not both. So it's just like the OR gate, but not both. So if exactly one of them, that's why it's exclusive OR. And then we can combine this with an inverter to get our sort of final boss here, an XNOR. So it's just like the XOR, but with a little inverter at the end. This is an exclusive NOR. And so this is the opposite of a XOR gate. So it is if both of the inputs are the same, basically. So if they're both off or if they're both on. And so what we can do is we can take all of these abstractions here. These are really just a few transistors under the hood. But we can take these logic gates and then we can combine them logically with different inputs and outputs and wire them together and then have computers do more and more complex things. And we can build whole systems that make just simple inputs and outputs of transistors make more complex behavior, such as add numbers, subtract, multiply, interpret code, store data, run a clock signal, and much more. Alright, so using those logic gates, we're going to learn how to get computers to add numbers. So in decimal or base 10 when we add numbers, just a super simple review here. Let's say we add 43 plus 89, and in base 10, then this is the ones digit, and then the tens digit, and the hundreds digit, right? And then we say 3 plus 9 is 12, so we have 1 carry and 2. And then 1 plus 4 plus 8 is 13, so we have 1 carry and then 3. And then 1, 0, and 0 is 1. And then we have our ones, tens, and hundreds, and these are all powers of 10. It's 10 to the 0, 10 to the 1, and 10 to the 2. So in binary, when we add numbers, let's say we have, I'm just going to throw some numbers down here. and we're in base 2. So instead of 1s, 10s, 100s, we have 1s, 2s, 4s, 8s, and so on. So 1 and 1 is 1, 0, which is 2. 1 and 1 is 1, 0. 1 and 1, 1, 0. And then 1, 1 and 1, we have 1, 1. 1, 1, we have 1, 0. 1 and 1, we have 1, 0. Then 1, 0, and 0, we have 1. And then so we have this number here. And so this is 1s, 2s, 4s, 8s, and so on. And then if we had a carry out of here, that would be the overflow. So let's make our adder. So for an adder, we'll have two inputs. We'll have input 1 and input 2. And then we'll have two outputs. We'll have the carry out, and then we'll have our sum. And so these can be 0, 0, 0, 1, 1, 0, or 1, 1. And so with all zeros, we have sum 0, carry 0. And then with either of them 1s, we have sum 1, and we don't have to carry. But then with two inputs of 1, we have 1 carry and then 0 sum for 1, 0, which is 2 in binary. And so if we wanted to make this, then we can see if we notice any patterns. So for example, just looking at the sum bit, then it's 1 if exactly 1 but not both. We already have a gate for that. That's exclusive OR. So we have our exclusive OR right here. And then this can output to the sum. And then for the carry out, then this is only on if both of the inputs are on. So that looks just like our AND gate. This is carry out. And then so we could have our two inputs going both over there and going in here. So input 1 and input 2. And then this is actually a half adder because it doesn't take into account the carry going back into it. So this would be like the first number we're adding here. So we can put this in a box. We can call it a half adder, and it outputs a sum, outputs a carry out, and then has an input 1 and input 2 both in. But if we want to have a carry in, then we'll need a new truth table and a new item here. So we'll have input 1, input 2, and then our carry in. And then we'll have our carry out and our sum. So again, these are our inputs, these are our outputs. And now we have 8 combinations here. And then for each of these combinations, so we're basically adding 3 different zeros or ones. So if they're all zeros, then we have 0 sum, 0 carry out. If we have exactly 1, then we're going to have 1 sum and no carry out. We could do that for this one here. And then if we have exactly 2 inputs, then we'll have 1 carry out and no sum. And then if we have all 3 inputs, then we'll have 1 carry out and we'll have 1 sum. And then so what you'll notice here is that the sum is only true if there are 1 or 3 of these that are on. So when one of these is on, or all 3 of them are on. So we could just say 1 or 3 for a quick note here. And the carry out is only true if there are 2 or 3 on. So we need to develop a circuit that has our 3 inputs. So it has input 1, input 2, and then carry in, and then correctly outputs the sum and carry into the right conditions. And so another way to thinking about this is the sum could be A XOR B, and then you can do that XOR C. So if A and B are both true, then C has to be true as well. And if both of these are off, then C has to be true. But if this gate is on, then C has to be off. So it doesn't allow for 2 and it doesn't allow for 0. And then the carry out is carry in and A XOR B, or A and B. So, because we need at least 2 of them, so if the carry in is on, then we can get if one of these is on but not both, or we can also get it if both of these are on. So that takes care of AB, AC, or BC, as well as AB and C. So what we're going to do here is we're going to wire these to an XOR, like this. And then we're going to wire C in with another XOR. And then this is our sum. And then we're going to wire A and B, or input 1, input 2 in here. To an AND gate. And then we're going to wire C to an AND gate that has the result of this. And then what we're going to do is we're going to OR the results of these, and this is going to be our carry out. So we have A XOR B XOR C right here, or input 1, input 2, and C input, carry input, all XOR'd there. And then over here, then we have the result of this XOR going into an AND gate here. So that's this part. And then we have A and B going in here. And then we OR them at the very end, like that. And so we can put this all in one box, and we can call this a full adder. And so we have our 3 inputs. We have our carry in. We have our input 1 or A. We have our input 2 or B. And then we have our 2 outputs. We have our carry out. And then we have our sum. And so what we can do is, let's say that we have a bunch of binary numbers we want to add. So we have this number. So we have the 1s, 2s, 4s, and 8s of that number. And we're adding it with the 1s, 2s, 4s, and 8s of that number. So we can hook this number up into a half adder. And then this has 2 outputs. This has the sum and the carry output. So I'll put the sum right here. And then we'll carry it out into here. And then so now we have our full adder with our 3 inputs. And then we output the sum here. And then we can carry over here. And then now we have another full adder with our 3 inputs. And we output the sum here. And then we'll output the carry over here. And then we have another full adder. And then we'll output the sum here. And then this last one, if there is carry, we'll call this overflow. And so that's just like in our previous example where we had 132. If we didn't have room for the 100s place, then we would be overflowing. And so now the result of this number, so let's say this is A1, A2, A3, A4, and this is B1, B2, B3, and B4. This is S1, S2, S3, and S4. So then we can say that this number plus B4, B3, B2, B1 is equal to sum 4, sum 3, sum 2, and sum 1. And then so whether or not this electricity is on or off is represented by adding binary digits for both of these. And then this is what we'd call a 4-bit adder, because we have 4 bits coming in and coming out. And so this is how computers add numbers, and we can make different logic gates for subtracting and for having a steady clock go in and storing data and all sorts of other stuff. But this is just one example out of many different examples of how computers can take logic gates, which are just transistors, and then make fully functioning math and logic units out of them. And we just keep abstracting and abstracting. So now we can abstract this whole thing into a box, and then we can call it a 4-bit adder. And then we can take in really 8 wires in here, and then we'll output 4, and then we'll also output the overflow as well. And so we can keep abstracting and putting things in bigger and bigger boxes, and then building up and building up. That's basically how computers are built from the ground up.